Okay, so today's notes are on cubes and volumes. Okay, so we want to start looking at volume problems. We've been doing surface area problems of 3D objects, but we're not going to start looking at the volumes of these, which tend to actually be a little bit easier than the surface areas. Okay, so just in general again, we want to think of volume. Okay, we want to think of volume as taking some area. Okay, so taking a square area. And then to give it volume, we want to give it some depth. Okay, so in general, we think of volume as area with depth. So let's take a look at some volume problems. So what's the increase in volume when a cube of side length 10 centimeters is increased by 2 centimeters? Okay, so if we take a look at a cube, let's take a look at the area first. We're taking a 10 centimeter area. So it's going to be 10 on both sides. And what happens to that area when we increase it by 2 centimeters? Okay, so we're going to go from a 10 by 10, 100 to 144. So if we think of it as percentage, a 20% increase results in a 44% increase. Sorry, 20% increase in length results in a 44% increase in area. So what happens if we do that the same with the volume? So imagine a cube to start with. Okay, so there's our cube, and then we're going to increase the sides of that cube by 20% in every direction. Okay, so it's going to be, we start with 1,000 cubic centimeters, so that's a 10 by 10 by 10 cube. So our volume initial is going to be 1,000 centimeters cubed. Okay, so what happens when we increase that volume by 2 centimeters on each side? Well, we get 12 times 12 times 12. So our volume final works out to be 12 times 12 times 12. So putting that into a calculator, we end up with 12 times 12 times 12 is 1728. So we go from, I'm just going to write this down, 1728 cubic centimeters. So a 20% increase in length results in a 44% increase in area and 73% increase in the volume. Okay, so the volume percent increase in the volume it ends up being a 72.8% increase in volume. Okay, so what we do is we take the extra 728 and we divide that by 1,000. So just want you to try to appreciate and understand that as we do increases linearly along a line, those increases do not appear the same when we think of area. Same with area. If we increase the area, the volume does not increase by the same percentage amount. So you have to be very careful with that. Okay, so let's take a look at another problem. The volume of the cube and the volume of the sphere are equal. Okay, so I have a cube, okay, and I have a sphere of roughly the same volume. Make that a little. Okay, so I've got a sphere of roughly the same volume. So will the sphere fit inside the cube, or will the cube fit inside the sphere? Or will neither happen? Well, if we think of this problem, if the sphere is fitting inside the cube, that would mean that has smaller volume than the cube, which is not true. And the same would be true of the cube inside the sphere. If the cube actually fit inside the sphere, then it must have smaller volume than the sphere, which is not true because they said they're equal. Okay, so neither will happen. So part B then is, if the volume of the cube is 8 centimeters cubed, what are the side lengths? Okay, so well, if I have 8 cubes, I can actually draw this. Okay, my picture's not great. If I draw this cube, there's going to be 8 cubes in here. Okay, I can actually count 8 cubes. There's going to be 4 here and then 4 along the back. Okay, so there's 8 cubes. So the side length ends up being 2 centimeters. Okay, so it's 2 centimeters, 2 centimeters, 2 centimeters along here. Okay, so there's my cube. It's a 2 by 2 by 2 cube. Now if I think of a sphere, the sphere's radius has to be different than that. Or if we think of the diameter of the spheres, can't be the same diameter. Okay, it's the side lengths there. So what's the radius of the sphere? Well, just figure that out. We actually need to know the formula for the volume of the sphere. So the volume of the sphere looks like this, and this is maybe the first time you would have seen it. It's 4 pi r cubed. Okay, we need to make cubes to make volume, and we're going to divide that by 3. So when we think of this, we can write the formula. That's equal to 8 centimeters cubed, and we're trying to actually find the radius. So this is a situation where we can use algebra. I need to find r, which means I need to undo a times by 4 pi. I need to undo a divide by 3, and I need to undo the cube there. Well, I'm going to do this in steps. So what am I going to undo? I'm going to undo the times, divide 3 by times 3. Okay, so I'm going to start with my 8 on this side. And I'm going to times 3 on both sides. Okay, so I'm going to times 3 times 3. So I'm going to end up with 3 on this side because those 3's cancel. Okay, I want to get rid of the divide times by 4 pi, so I need to divide by 4 pi. I need to divide by 4 pi. So I'm going to end up with those are going to cancel. The 4 pi is going to end up on the bottom here. Okay, so what's left on the left hand side here? I'm just left with r cubed. Okay, so then I'm going to simplify that before I do another step. I don't want to do too many steps at once. 8 divided by 4 times 3 is 6 over pi, and that's centimeters cubed. That's how many cubes I have. If I want to undo cubes, I can undo cubes with the opposite, which is a cube root. If I cube root one side, I have to cube root the other side. So my radius works out to be radius equals, oops, there should be a cube root there, the cube root of, make a little bit nicer looking cube root of 6 over pi centimeters is going to be my radius. So if I work that out on my calculator again, I'm going to have cube root of 6 divided by pi. And that gives me about 1.25. It's approximately equal to 1.25 centimeters. Okay? So the diameter would be about 2.5. My diameter has to be bigger than this cube because it has to have the same volume.